Okay, now move on to this, and this is the full screen. Okay, hello guys, this is Vishnu Saraswat, working as a senior research fellow at Banaras Hindu University. Today guys, we are talking about the Lagrangian dynamics. So guys, we will start our topic. So what is what is Lagrangian mechanics? Okay, so what is Lagrangian? Lagrangian is a function of generalized coordinate, generalized velocity and time, and we can also written as a q replaced by any variable like x. Here represent only position, so we can written as a x, y, z or any other variable. So here the x represent the position, x dot represent the velocity and t represent the time. So Lagrangian gives this formulas and which is a function of x, Lagrangian velocity and time, which is equal to kinetic difference of kinetic energy and potential energy. So Lagrangian is equal to the difference of kinetic energy and potential energy. So uh, many textbooks written the kinetic energy as T and potential energy V. So we can simply written L is equal to T minus V. So here one thing I will clear for you actually x dot. Here the x dot is velocity and x is position. Okay, so dot represent the time derivative, simply time derivative. If we put p dot, that means dp by dt. Dp by dt means force, rate of change of momentum. So if we put dot on any variable, so that convert into the time derivative of p, time derivative of position, that means uh, velocity, time derivative of velocity, that means acceleration. So dot represent only here time derivative. So now we take a example of free fall particle like this. This is the particle which have mass m under gravity g minus 9.8 meter per second square. So the height from the ground of this particle is like x, or you can take x, y and h. Also you can take the height h, but for my convenience I took x. Okay, so now we are talking about kinetic energy of the particle. As you know about the kinetic energy, so half mv square. So we can replace the v as a x dot. As you know, the dx upon dt. So we can write dx upon dt. Velocity equal to x dot, and dot represent the time derivative of position, which is known as velocity. So now we can write our kinetic energy is half m x dot square. And um, now we are talking about potential energy. Potential energy is mgh. So mgh is a height, so we represent height as a x. So we can write here h is x. So now we put these kinetic energy, these value of kinetic energy and potential energy, and we can put that values in this equation 1. So now our Lagrangian looks like mx dot square minus mg x. Okay, so this is our second equation. Okay, so for the sake of our convenience, Lagrangian introduced the general equation of motion. So general equation of motion, general equation of motion, which is written as time derivative of partial derivative of Lagrangian with respect to velocity and partial derivative of Lagrangian with respect to position equal to 0. This is given by Lagrangian. So here is the Lagrangian, or as I told you, the Lagrangian is a equal to the difference of kinetic energy and potential energy of object or any particle. So now we need partial derivative of Lagrangian with respect to with velocity, and here is a we need partial derivative of Lagrangian with respect to position. So we calculate the partial derivative of Lagrangian with respect to velocity by the help of this equation. So we can calculate. So del over del x dot. So we can put here del upon del x dot, and we put the value of L m x dot square by 2 minus mg x. So here we take the derivative of mx dot square by 2. That means mx dot 2 is simply uh, in front of m, and 2 and 2 cancel out, and this value is not a function of velocity, so this value going to 0. So now we got the value of del over del x with respect to velocity is mx dot, and then we again calculate the partial derivative of Lagrangian with respect to position, like dl over del x. So del over del x and m x dot square by 2 and minus mg x. So this is a position, but here is a velocity, so this is not a function of position, so this is simply 0 and this is equal to, so we can take the derivative of this mgx, so we got minus mg, so del L over del x. So these values and a and b values we put in this equation 3. So a and b values put in this equation, so our equations looks like time derivative of, and this value mx dot, so we can simply put, and del over del x, so we can simply put this here, so this is minus k mg equal to 0. So m is independent of time, so we write m as it is and x change into the x double dot here, and minus minus plus, so we can write mg equal to 0. So what we got, this equation, we got this equation, so we can cancel out the mass, or we can divide the whole equation by m, so we got m x double dot, so m cancel out, so we only left x double dot plus g equal to 0, or we can simply write x dot equal to minus kg. or x double dot represent here the acceleration. Actually, I already told you x dot is a velocity, and then again we put on dot on x dot, that means x double dot, or x double dot means x the time derivative of x double dot represents the time derivative of velocity, so which is equal to the accelerations. So what we got the acceleration is negative. Acceleration is negative of our object which is uh, fall under the gravity. So, and we can also calculate from this, uh, we took the integral of this equation, we got the velocity, then again we took the integral, again we will take the integral of this equation, so we get the position of the particle. So here is the particle, and which going like under the gravity, so minus sign that indicate that this is hmm, fall under the gravity. So today I think it is enough for today, and in next video we will talk about the Atwood machine, and which we will calculate by the help of Lagrangian equations. So, and the next further videos we will discuss about the how the plane change into the polar coordinate and spherical coordinate, and any others example we will take. And for today I think this is good for today lectures. So I hope you will enjoy this video.